and the session is on, the theme is measurements needed for resource evaluation. On that note, it's 11:30. Shuai, are you available?
Yeah, I'm here. Can you hear me?
All right, go ahead. We hear you loud and clear. Thank you.
Oh, great. Next slide, please. Yeah, as we heard a lot of talks today, so the distribution and abundance of surface exposed ice is important to assess the water ice as in resource utilization. Many observations suggest that lunar surface ice is very patchy. I'm not sure this is due to the heterogeneous content on the surface. The lower water ice cannot be well resolved by the current data site. Here I'm showing one example at the lunar south pole. When we lower the threshold for detecting water ice, we see 2.5 times more pixels showing ice content, lower ice content, as shown as the red pixels. In this spectral plot, I'm showing like the water ice spectral compared with the lunar regulus. You can see one of the absorption near 1.3. This is like only show up at a very high ice content, while when it is low, you don't see this absorption. And when the ice content decreases to a few %, you won't be able to see the 1.5 micron absorption. You will only see the 2 micron. But unfortunately, the current data set cannot resolve it. So anyhow, the high ice content will be very important for ISRU, while the low ice content can also be very important because possibly it's more widely spread and also be important for science exploration. For example, how do they survive on the surface by gardening and irrigation for a long time, and also their sources, whether it's possible from like solar wind or impact delivery, in a very short time, or it's just a churning of the degassed water buried a long time ago. And also, it's interesting to examine the spatial correlation with both surface features and also the subsurface. Next slide, please. Yeah, if we want to use reflectance spectroscopy to detect surface ice on the moon, maybe the best part will be using the near-infrared feature. As we can see in previous experiments, people show that the albedo doesn't very much when the ice content is less than 40%. So particularly in the lower phase angle observations shown in the left plot, you can see even after like the ice content increase to 70%, 80%, you don't see much change. And at a higher phase angle, you can see a significant change. This is due to a strong forward scattering, but that's put limits on the orbital observations. You have to do the observation at a very high phase angle. While on contrast, if you look at the near-infrared feature, it varies strongly as you increase the ice content. And it shows in our simulation and experiments that the ice content, we can detect the ice content as low as like 0.1% using band depth near 2 micron. And recently, my students, Nina Castro, did some experiments showing that the 2 micron band depth doesn't change much with the particle size from like a 20 micron to over 200 micron. That's applicable to the lunar surface. And also the 2 micron band depth doesn't change much with the phase angle from like very low 0 phase to over 100 degree. So high quality near-infrared data covering the 2 micron absorption feature will be great to accurately map the surface exposed water ice on the moon as low as like 0.1%, unless you will have like, high quality data. Next slide, please. And there are other interesting spots on the lunar surface associated with like ancient lunar volcanism, like at a lower latitude can be also important for resource utilization and science exploration. For example, the red circle region at the periplastic bodies. They can, although the water content is very low, like 0.05% to 0.1%, but in total it can be like millions of tons because it's a large area.
And we need to move on. I hate to do it.
Sorry.
But
Okay.
4 minutes.
That's almost it. Thank you.
Last thought. Okay, fine.
Yeah.